So in this video, we're going to talk about laser dynamics. And what exactly do I mean when I say dynamics? Well, let's say that we've got a laser, and I'm just going to represent this by this diode circuit symbol here, and I'm driving a certain amount of current into it, I. Then we know that the laser is going to be emitting a certain amount of power, or equivalently, there's going to be a certain number of photons inside the laser cavity, and some of them are going to escape every so often, and that's given by the photon lifetime, tau p. But up to this point, we've been doing steady state analysis, which means that nothing here is changing with time. So this current, which I'm going to represent by I naught, is constant with time. Similarly, the output power is constant with time. And this might be great if you're doing stuff like illumination, where you want a constant power. But for most applications with lasers, like communication and other really cool things like ultra-fast laser pulses for like things like fusion research. If you're interested in these sorts of things, this is going to require your output power to change with time. So if you're interested in digital communication, for example, you might want the output power to look something like this. So it goes from very low output power to very high output power. And so you can transmit a stream of bits in this way. And we engineers, we're greedy, so we want to make this laser go as fast as humanly possible. We want to transmit as much information as we can, or pack as much energy as possible into a very short time period. And so to do that, we need to understand how fast this laser can operate. And that's given by its frequency response. So if instead of just driving it with a constant current, we're driving it now maybe with a constant bias current, but also with a sinusoidal excitation, and I'll just call that I1, e to the j omega t, we want to know the fastest omega that this laser can respond to. And that, of course, is given by the frequency response. So maybe at a certain point, the laser, say, call this frequency omega naught, the laser just can't go as fast as we're asking of it. The number of photons, maybe the number of photons inside the cavity can't build up quickly enough for us to get the output power that we need when we inject a certain current. But we'd like to figure out exactly what it is limiting our lasers so that we can figure out how to engineer them to get the fastest possible frequency response, or push this corner frequency out as much as possible. So maybe if we're clever, we can make this laser operate really, really fast. So now the question is, how do we figure out this frequency response? Well, all we need to do is use the differential equations that we've learned so far. So we've got two differential equations, one which is describing the number of photons inside the cavity, and the other one which is describing the carrier density. And so this is the classic thing that we're used to dealing with in semiconductor physics. It has units of per volume, or most commonly per cubic centimeter. And I've been doing, the number of photons is just a pure number. We're not dealing with densities. So where do photons come from, or what is the rate equation? Well, we've gone over this in previous videos, but just recapping here, photons can come from a few different places. They can come from stimulated emission, and this is the primary source that we're interested in with lasers. They can also come from spontaneous emission, so spontaneous emission, and we can lose photons when they escape out of the sides of our device, so when they escape out of our mirrors. And this was described by a certain photon lifetime, tau p. Now, when we're driving these lasers really fast, we're generally using a lot of power. And so we're going to be able to ignore this spontaneous emission term in our rate equation. And so I'm just going to erase that. We're just going to ignore it completely. And so let me rewrite the number of photons, or the photon lifetime term here. So we're still losing photons out the side of our mirrors, but we don't have to worry about the added spontaneous emission. Now, for the carrier density, we also have gone over this rate equation, But where do the carriers come from? Well, first they come from injected current. So they come from whatever current we are sending into this laser. So this current is showing up as electrons, which travel through this wire into our laser, and that's going to increase our carrier density. So that's one of the sources of electrons. We can also lose electrons to recombination. So we can lose them to stimulated recombination. We can also lose them to ABC recombination, or the Shockley-Reed-Hall recombination, spontaneous emission, and Auger recombination that we've talked about previously. And we can lump this all into our ABC approximation. Now, what we're ultimately trying to solve for is we're trying to solve these two differential equations to give us a frequency response, or a transfer function, the output power divided by whatever current we're going to inject into the system. And we're going to assume that we care about this we care about the small signal deviation for our laser. So we're going to have a certain bias current, I naught, and we're going to apply a certain perturbation to that, delta I, or a certain small signal. And this is in general going to be of the form I1 e to the j omega t, because we can apply, we're generally applying sinusoidal excitations. If we're not, we can just use Fourier transforms to make it into a bunch of sinusoidal excitations. Now, we also know that the number of photons is related to the output power just by the number of photons that escape per unit time, which is given by the photon lifetime, multiplied by the energy per photon. So if we can figure out a transfer function in terms of the number of photons divided by the current, then we can figure out what the output power is, because it's just proportional to the number of photons. So now let's set up these equations to be solved. So let's figure out exactly what we need to do to make these tractable. And this is probably the most challenging part. The rest is just math. So first of all, we need to expand all of these recombination terms. So we know that our ABC recombination, this is the simplest of them all, is just AN plus BN squared plus CN cubed. And you can interpret this as a Taylor series, or each of these as independent recombination mechanisms. We also, in a previous video, investigated what the stimulated emission term was. This, we said, was just whatever gain we've got in the material times our photon group velocity times the number of photons we have, or the density of photons in our entire cavity. So we need to divide this thing by the photon volume. But we can also rewrite that in terms of gamma and the active region volume. So the active region volume is something physical, it's something we can measure, and gamma is just this fudge parameter, our confinement factor. And there's one more awkwardness we have to deal with, because remember that the gain is actually a function of the carrier density, n. So this is going to make our lives a little more difficult, and when we deal with nonlinearities, it's going to make our lives way more difficult. But we need to also deal with this. And we know that we can approximate the gain using this logarithmic approximation. So we have a closed form expression for the gain in terms of this parameter G naught and our transparency carrier density N, NTR. And so we have everything we need. Now the last bit is just that we want to know how this system responds to a small signal change. So we're going to have the current be some DC component, I naught, plus some AC component, delta I. And in general, this is going to be of the form e to the j omega t. Now, by adding this AC current, we're going to cause everything to have an AC component. So our carrier density is going to have an AC component. Our number of photons is going to have an AC component. Everything in these equations is going to have an AC component to it, or a small signal component. Even our stimulated emission is going to have some DC component and some AC component, as will our ABC recombination. So our ABC 0, and I'm denoting the DC components with a 0 after them, and the AC components with a delta in front of them. And in the next video, we're going to start a full frontal assault on these equations, and we're going to solve them, and we're going to figure out what the transient response of a laser is. So I hope you enjoyed the video. If you did, please give it a like down below. Also, if you have any questions or comments, please feel free to post those down below, and I'll try to get back to you as soon as I can. And thanks for watching. I'll see you next time.